Okay, it is now time to start talking about volumes. So we've been doing area, and now we're going to take different regions and we're going to revolve them around the x-axis or the y-axis or some other line, and that's going to give us a solid, and so that's why they're usually called volumes of solids of revolution. And we're going to learn a couple of different ways to do that, and today we're going to start with one that's a little bit different that has to do with if we know what the cross sections look like. So first question would be, what in the world's a cross section? Well, if you think of a loaf of bread and then the bread's all cut into slices, and that slice is what we call a cross section. And so a cross section is really just the intersection of a plane and the figure. So it'd be like if you just cut across of it and then you look down at the face and to see what it would be. So the basic idea, you're going to have a region and it's going to be defined by some functions, so that will enclose the region, kind of like we did with area. And then you're going to graph that, and then we imagine solid slices coming out from that. So we're going to look at a demo that's really nice, that shows you a better idea of what those cross sections look like. And it's on your notes. If you want to look at it later, you can see that. But basically, looking at this, the x and y axis are kind of like they're laid down flat, and so these cross sections are coming up off of that. So these cross sections are all semicircles, and then that thickness there, notice it's going across the x-axis. The x-axis is laying down, so the thickness is delta x. So it's like what we did with area. That's going to tell us that that width is delta x. So we're going to do things in terms of x. So let's look at a different one. Oh, maybe. That was semicircles. So here's one with where the base is an equilateral triangle and we have square cross sections. So it's just a bunch of squares being built up, only technically they're prisms because they have a height. And so again, that width is going in the x direction, so this one would be like something we do with the x. Now we probably won't do one necessarily like that, the way that one looks, but let's see what else. And here's just one more example. So here is cross sections that are against squares, and there's a function there that's a part of a circle, a quarter of a circle. And so if you look carefully at it, you can realize that the length of the side of the square is just simply going from the x-axis to the function, and so that's going to be the length of your side. All right, so let's start practicing, and the fun part of this is the drawing. So you're gonna want to practice that, but first let's look at just some cross sections that someone else has drawn, and then we'll talk about that. So basically, you're going to have all these prisms. So in this case, we have basically a square prism, and you're going to have a whole bunch of them, and you're going to add them up. Well, we use calculus to do that because they vary. So to find the volume of this particular square slice, and this one is shown to be dx for the thickness, and so very often that's the way it will be. We'll most of the time have the width be across the x-axis, so that it's dx. So to find the volume of this particular slice, it's going to be basically a prism, so it's going to be whatever the area of the base is, which is the square, times that dx, because that's your little width. Well, the area of a square here, the side is square, is x, so it's just going to be x squared dx. Now that's for that one individual one, and then of course when we're doing a shape where all the squares are changing, then that x value will change a little bit. All right, so here's a semicircular slice, again shown with dx being the little bit of the width. So again, the volume of this slice is going to be simply the area of that semicircle times dx. Well, the area of a circle is pi r squared. It's a semicircle, so we need half of that. So it's half pi r squared dx. Well, but we need to talk about what r is. We don't want to answer this with an r in it. We need to have r in terms of x. Well, if we look at our picture, it's x all the way across there. So that means r would be from the center out. So r would equal 1/2 x. So we would simply replace the r with 1/2 x, and then that would be fitting with our function here. So we would have 1/2 times pi times 1/2 x squared dx. Well, a half times a half is a fourth, times another half gives me an eighth, and then we have pi and then x squared dx. And so that would be the volume of this particular cross section. So we would also need to be able to figure out volume if we had different shapes like that we already know how to find, like right triangles, equilateral triangles, isosceles triangles, things like that. So those shapes might be involved too for this part where you're finding the area. And the process is the same. Okay, so let's look at an example, and I'll do the best I can to draw this, and on your paper you have some multiple choice. And so we'll practice a little bit of that and how we want to be careful before we choose that answer. So here, the base of the solid is the region that's enclosed by the parabola, the line x equals 1, and the x-axis. So first let's draw it just your normal direction. And pretty much every time it's a good idea to draw these two different ways that I'm going to draw this. So you have a parabola that's 4x squared. So that's just the x squared parabola a little steeper. We have the line x equals 1, so I'm just going to put it out here. It doesn't really matter that much about the scale here on this one. And also the x-axis. So my boundary here is this. This is my base right here. That's the shape. That's the base of the region. And so we're going to have plane sections. All of our sections are slices that we're going to make are perpendicular to the x-axis, and they're squares. So we're going to redraw this where it looks like the perspective, where it looks flat. So here's our x and y-axis, and so we're going to draw our parabola like this, and our line x equals 1 parallel, and then oh, that's going to really make it hard to see our region. I guess I better draw it bigger than that. Try that again. And you're going to do the same thing when you draw it. It's not going to be that easy, and you're going to have to just practice. So let me draw it way wider than it really is to help it see it a little bit. And then we have the line x equals 1. Well, I didn't make it any bigger, did I? Try again. Make it go up faster, I guess is better. Okay, and then the line x equals 1, and we'll make it out further. Okay, so there's our region. So basically your squares or cross sections are coming up out of that. So they're going to be coming up this way, and this isn't going to look square. They're going to look rectangular, but it'll be easier for me to draw. And so you'll have other ones coming up out of this. So you have to imagine them coming up off the page and coming up out, and there are your slices. Well, when they're drawn over here, they're going to be much harder to see when you do it this way because they're coming out at you. So it's really hard to draw it over on this drawing. It's a little easier here where we've kind of drawn it flat. Still kind of difficult to see, but we can see that right here, if we take this slice, we can see that the width is going along the x-axis. So your width here is going to be delta x, or dx. So we're going to do everything has to do in terms of x. Now, if that's a square, which these don't look very square, but imagine that this is the same length as this, as the whole thing. So it's a square. Well, the height of your squares, now if we go back to the first picture, this is where we can kind of tell better. If we draw the square, we know that we'll have a square right through here that's going to come out of the page, basically. And you would have other squares and other squares. Well, you can see better here that this right here is going to be your height, or the length of the side of a square. And so that's the function. So to go this distance along the side is just the function value for each one of those squares. So that means a volume of a particular slice is going to be the area of a square, which is 4x squared is the length of one side, and then you have to square it because it's a square, times your dx. Well, if I want to find the actual volume, the true volume, then I have to add up infinitely many of those and let the slices get thinner, just like we did with area with rectangles. Now you just have to imagine those 3D figures doing the same thing. And so we're going to then integrate it, and we know everything's in terms of x. So x runs from 0 to 1. Easy to figure out that intersection. And it's this function, so that's 16x to the 4th, if I go ahead and square it, dx. So then I would want to go ahead and do my integration. And so I will get, I can leave the 16 out here, and it's going to be x to the 5th over 5 from 0 to 1. If you plug in 1, you'll get 1/5 times your 16, and plug in 0, you get 0. And so now you can see that your answer there is D. And just keep trying to visualize these and go back to that website too, which really helps you see that, how those come out of the page a little bit better. All right, so let's go to this example, example 4. So now we're bounded in the first quadrant by the x and y axis and a line. Okay, so let's get that drawn. So we know in the first quadrant, so I'll mostly draw over there. So probably easiest to solve that line. So let me do that over here. Solve this for y, makes it easier to graph. So that's 8 minus x. So y would be 4 minus 1/2 x. So that's one way to graph it, or we can also, actually it might be easier just to go by the intercepts here. Just count by 2's over here. So actually your intercepts, if you set x equal to 0, you'll get y equals 4. So this is going to cross at 4. And if you set y equal to 0, you'll get x equals 8. So I'm going to count by 2's here and 1's here. And so there's my line. So that's part of the boundary. And then it said the x-axis and the y-axis. So here's your x-axis and your y-axis are also boundaries. So the shape that I have right here is the base. Oh, doesn't want to switch for me. All right, so this is your region here. This is your base. And so again, difficult to see, but it says here that the cross sections are semicircles. So basically that means that you've got something here and out comes the semicircle, and then you have another one and out comes a semicircle. Now obviously these are going to be closer together, but to draw them this makes it a little easier. So you have all these semicircles going along, and then again our goal would be to make an infinite number of those. Well, let's go ahead and draw it a little bit to the side, a little diagonal bit of one here again. So this is 8 and 4. So we have our line. And so visualize this kind of laying down, and now we have our semicircles coming up like this. Okay, so here's your semicircle regions. And again, the width goes along. If you look back at this original picture, you can see that the width of the little slices would be this direction. So they would be dx or delta x. And then you want to find the area of a semicircle and multiply it times dx. Well, to find the area of a circle, we need to do pi r squared. So the volume of a slice is going to be the area of a semicircle, so that's going to be 1/2 pi r squared times your delta x. Well, just like the example we did earlier, we don't want to leave r like that, so we want to figure out what r actually equals. Well, the height of one of these, again, why it's easier to draw it in this direction, this height right here, this length is the diameter. So this is the diameter for any particular semicircle, and it changes depending on where it is. Well, that distance is just the function. So the function was, when we solved it for x, was 4 minus 1/2 x, or solved for y. So that is 4 minus 1/2 x. That's the diameter. But we want the radius, so we need to take half of that. So that means we're going to have 1/2 pi, and instead of r, we're going to have half of 4 minus 1/2 x, which would be 2 minus 1/4 x, whole thing squared, dx. So this here, our radius is this right here. So the diameter is the length from the x-axis up to that line, and the radius would be half that. So there's half of that. Now, if we look, this is a good example of something that you should always do on your AP test. If you'll look at the answers there, A through E, on your notes page, you'll notice they're all decimals. So that would tell you that you need to simply set this up and put it in the calculator. This is not one that we would do by hand. So again, the idea is this is the volume of one single slice. So if we want the actual volume, we will need to integrate, and it's again in terms of x. So it ranges from 0 to 8, and then we just wrote this function 1/2 pi 2 minus 1/4 x squared dx. No reason to simplify that because this is a calculator problem. So use the calculator, type that in. Remember your shortcut of shift plus sign to get your integral sign. Type everything in just like it is, and you should find out that your answer is 16.755 as you do that on your calculator. I'm not going to do that on this video. Just ask if you ever need help with that in class. All right, let's do our last example. So this time we have the base of the region enclosed by 2 minus x squared, so that's a parabola, and the coordinate axes. And then here it says if every cross section is perpendicular to the y-axis and they're squares, then find the volume. Well, so this time we're going to have this will have to do with delta y then. So let's go ahead and draw this. This won't happen very often, but we want to practice it for when it does. So to draw this graph, it's 2 minus x squared. So it's going to intersect the y-axis at 2, and it's a parabola that opens down. So this is the graph that you're going to have. And it's in the first quadrant, and it's enclosed by the coordinate axes. So basically, this is your region right here. And then we have cross sections that are perpendicular, this time to the y-axis. So your cross sections are going to all be going this way. This is what they would come out. And again, they're supposed to be squares, which is kind of hard to draw it that way here. Okay, but that's what your cross sections are going to look like. You got to imagine looking down at that. So again, let's draw it kind of squished to the side so that it's a little easier to see that perspective. So if we draw our parabola, and then our cross sections then go perpendicular to the y-axis. So they're going to go like this. And this time your width is going in this direction. So imagine it being wide this way. So it's going along the y-axis for your picture. So imagine it, your width going that way. And so here's your shape. Okay, and the width is going along the y-axis. Okay, so this same exact process, the difference is just the width is going up and down. So this is delta y for the width of my little slice. And so everything in the problem just needs to be in terms of y. That's it. Otherwise, everything else is the same. So we were given the function y equals 2 minus x squared, so we're going to have to solve it for x to get it in terms of y. So that's going to give us x squared equals 2 minus y. Square root both sides. Now technically we get plus or minus 2 minus y, but remember it's only the part in the first quadrant, so we can get rid of our plus minus there because it's only the positive part that we need. So that's what x equals. So the volume of a single slice is going to be, well, if you look back over at the first picture, we can see that the width of our square this time is the function going over to the y-axis. So it's just going to be the y function. So here you're going to have and everything in terms of y. So we're going to integrate from 0 to 2 because we know it intersected up there at 2. And it's going to be, oh, I guess we don't want to integrate yet. Let's just do the volume of a slice. And so that's going to be the function, which was 2 minus y, square root of that, whole thing squared, times your dy. Now let's do the total volume, which is integrating 0 to 2 of that function. Well, square root squared, you're just going to get 2 minus y and then dy. And so this time we don't even have to go any further, because if we look at the multiple choice on your notes there, you can see that all we were supposed to do was set it up. That's also a very common AP question, because plugging it in your calculator is no big deal. So we can see that the answer there is B. So this is the first look that we have at volume. This is very different than what it will be when we revolve things, a little bit different, but this is a very typical AP question, so be sure that you understand the basic concept.